So, what if I told you there's an invisible instruction manual that governs literally everything? From a tiny apple falling from a tree to a massive planet orbiting the sun. For the longest time, we all thought those were two completely different worlds with two totally different sets of rules. But they're not. They all follow Newton's laws of motion, the absolute bedrock of our physical world. Let's get into it. For centuries, this was one of the biggest questions in science. It just seemed obvious, right? The stuff happening up in the heavens and the stuff happening down here on Earth, they had to be playing by different rules. But one single brilliant insight would connect them forever, and in doing so, create the first truly universal laws of nature.
But before Newton gave us the answer, the big why, scientists were actually wrestling with a different puzzle. See, the story doesn't start with why things move, but with a really precise description of how they move. And this timeline, it reveals something really important. We're talking decades before Newton published his masterpiece, another giant of science, a guy named Johannes Kepler, had already mapped out the movement of the planets with just incredible accuracy. So Kepler, using just mountains of observational data, figured out that planets don't move in perfect circles, they move in ellipses. He could describe their speed and how long their orbits took with pinpoint math. He gave us the what, but the why? Well, the why, the actual force pulling all the strings, that was still the single biggest mystery in all of science. And this is where Sir Isaac Newton walks onto the scene. And he wasn't just going to solve the little puzzle of the planets. Oh no. He was about to write a single set of rules for the entire cosmos, for everything on Earth and everything in the heavens.
First up, you've got the law of inertia. You can think of this as the universe's default setting. Basically, everything just likes to keep doing what it's already doing. If it's sitting still, it wants to stay still. If it's moving in a straight line, it's going to keep doing that forever, unless some outside push or pull messes with it.
Okay, so how do you change that default state? That's the second law. This is the rule for causing change. The more force you apply, the harder you push, the more acceleration you get. But, and this is key, the more massive something is, the harder it is to get it to accelerate. It's this simple, elegant, powerful equation that just explains how you get things moving.
And finally, the third law. And this one is so important. Forces are never lonely. They always come in pairs. When you push on a wall, that wall is pushing back on you with the exact same amount of force. Every single time. And this was the masterstroke. This was the outside push or pull that tied it all together. Gravity. That was the answer to Kepler's why. For the very first time in history, one simple, beautiful law explained why an apple falls and why the moon orbits the Earth. The same force, governed by the exact same rules. Newton unified the entire universe.
Okay, but these laws aren't just for planets and apples, right? This isn't just some abstract, old-timey science. They govern our world every single second in ways you might not even realize. Let's see them in action.
Think about a car airbag. When a car slams on the brakes in a crash, your body wants to keep right on moving forward because of inertia. The airbag explodes outward to provide an opposing force, slowing you down safely. That's a life-saving application of the first law, right there. Or how about a rocket? How does it move in the total vacuum of space where there's nothing to push against? It's the third law. The rocket violently shoves hot gas out of its back. That's the action. In turn, the gas pushes the rocket forward. That's the equal and opposite reaction. And sports? Oh man, sports are basically a giant playground for Newtonian physics. Kicking a ball is pure F equals ma. A swimmer pushes water backward to move forward. That's action-reaction. Every jump, every throw, every tackle, it's all a demonstration of these fundamental laws. But as powerful as they are, it turns out they have their limits. For over 200 years, Newton's laws seemed absolutely perfect. It looked like he'd figured out the universe's clockwork. But as our tools got better and we started peering into the extremes, we started to see the edges of his beautiful map, the places where the rules, well, they started to change. This brings us to a really cool idea called the Newtonian limit. The easiest way to think about it is like a zone. The zone where Newton's laws work flawlessly. And that zone covers almost everything we experience in our daily lives. Things that are big enough to see, moving at normal speeds, and not hanging out next to a black hole. And you can see those boundaries so clearly here. Newton's rules are the king of the familiar world of baseballs and cars and planets, but when you get to the extremes, the incredibly tiny, the unbelievably fast, or the mind-bendingly massive, the universe starts playing by a whole different set of rules.
And that discovery, finding those boundaries, it opens the door to the next great chapters of physics. And none of it would have been possible without the incredible foundation that Newton built for us.
So, when you start approaching the speed of light, where you're dealing with the intense gravity around a star, Newton's laws need a bit of an upgrade. And that upgrade is Albert Einstein's mind-bending theory of relativity, where space and time themselves can stretch and warp. And if you go in the other direction, you zoom way in to the world of atoms and the particles inside them, well, that's where things get truly, truly strange. The predictable clockwork universe of Newton just dissolves into the bizarre probabilistic world of quantum mechanics.
In this realm, particles can literally be in many places at once. They can be both a particle and a wave at the same time. They can even tunnel straight through barriers that should be totally impossible to cross according to classical physics. F equals ma just doesn't work here.
But here's the thing, finding these limits doesn't mean Newton was wrong. Not at all. In fact, it's the ultimate proof of how profoundly right he was. He built the foundation that all of modern physics stands on. As he famously said himself, he only saw further because he was standing on the shoulders of the giants who came before him.
Newton's laws gave us a framework that worked beautifully for centuries, and they still describe our everyday world with almost perfect accuracy. But it leaves us with this incredible question, right? Which of our current universal rules are just waiting for us to find their limits? What new mind-bending physics is waiting for us just on the other side?